Hi everyone, my name is Liubov, but I go by Nikki, and today I'm really excited to present the research Pouya and I have been working on during our time at Stanford. When in doubt, ask. Generating answerable and unanswerable questions, unsupervised. A bit about us. I graduated from Stanford with a master's in computer science, and Pouya is a PhD candidate at Stanford in civil and environmental engineering with minor in computer science. I included our LinkedIn handles in the slides, so please don't hesitate to reach out if you want to learn more about this research or about us. Alright, let's dive in and look at the table of contents. In the introduction section, we're going to go over some background information relevant for this study. In the methods section, we will get into the details of generating answerable and unanswerable training examples from a Wikipedia dump. Experiments section is going to go over conducted experiments, metrics used, and obtained results. Finally, discussion section is going to outline the takeaways, limitations, and suggested directions for future work. So let's start with the introduction. Question answering is a field that enables machines to answer questions asked in a natural language. Modern deep learning models have enabled computers to exceed humans in some question answering tasks. BERT and FPNet models trained and evaluated on Squad 2.0 dataset are examples of this. One big caveat of these advanced models is that they require massive human-labeled training sets, which are expensive and time-consuming to generate. The problem exacerbates with language models trained for languages other than English, which have more limited man-made resources. We're hoping to alleviate the need for the expensive human-labeled training examples by exploring ways to boost the performance of QA models using synthetic data. Our hypothesis is that for question answering tasks, augmenting human-made data with synthetic data helps train models with better performance than that of models trained only on human-made data. More specifically, we're going to validate this hypothesis in extractive question answering by looking at performance of a BERT model trained on different combinations of human-generated data and synthetic data. The human-generated data comes from Squad 2.0 dataset, and the synthetic data comes from the machine-made answerable and unanswerable question-answer pairs, which we generate ourselves using unsupervised methods. Let's briefly zoom in on the Squad dataset we're going to be using in this study. Squad stands for Stanford Question Answering Dataset. It consists of paragraphs sampled from Wikipedia and questions about these paragraphs posed by crowdsourced workers. The answer to each question, if it exists, is a span of text from the corresponding paragraph. Squad 2.0 consists of about 100,000 answerable questions and about 50,000 unanswerable questions. To perform well, the model must not only correctly identify the answer from a paragraph, but also determine when a paragraph does not have an answer to the question and abstain from answering. Here's an example of a Squad question-answer pair. It consists of a Wikipedia paragraph, a question about the paragraph, and an answer to the question. Note that in this case the question-answer pair is answerable because the answer to the question can be found within the paragraph. But if the question was unanswerable, we would leave the answer blank. In this work, we take a generative model from Lewis et al., which can generate answerable question-answer pairs based on clause translation, and extend it to generate unanswerable question-answer pairs. Then we feed the synthetic data combined with Squad 2.0 dataset in various proportions to the BERT model and look at F1 and AM scores across different input combinations to compare performance. Per our hypothesis, we expect the language model trained on augmented dataset to outperform the model trained solely on human-made data. Now let's get into details of synthetic question generation. We started with the unsupervised model by Lewis et al., which is able to generate synthetic answerable question-answer pairs. Then we refactored this model to produce question-answer pairs in Squad 2.0 format and extended the model to preserve the information regarding a paragraph belonging to a certain article, since before this change, the model treated each paragraph as a standalone article. To generate unanswerable questions, we have shuffled the questions within the same article. This ensured that while the questions were unanswerable, they were still somewhat relevant to the context of the article to make it harder for the model to distinguish between answerable and unanswerable questions. Let's go through the pipeline of generating an answerable question with a model using a concrete example. First, we start with a sentence that we input into the model. Then, we use named entity recognition system to identify noun phrases in the sentence. In this example, the noun phrases are Albert Einstein, Germany, and the date of birth. These named entities form a set of potential answers, and we pick one answer at random from this set. For the sake of example, let's say we pick Germany. Then, we use an English syntactic parser to identify a subclause around the answer. In this case, it's just the whole sentence. We make a clause statement out of the subclause by masking our answer, Germany. Afterwards, we use unsupervised neural machine translation system to convert a clause statement into a natural question. Combining the generated question with the initial paragraph and the chosen answer gives us the answerable question-answer pair. Now that we went over generating answerable question-answer pairs, we're going to look at the pipeline for generating unanswerable question-answer pairs. We start with a Wikipedia dump consisting of a bunch of articles. Each article contains one or more paragraphs. We input these articles into our refactored model from the previous slide and generate answerable question-answer pairs. Then we erase the answers, detach each question from its corresponding paragraph, and assign a question to another paragraph from the same article at random. This is how we end up with unanswerable question-answer pairs. Now that we have a way of generating answerable and unanswerable question-answer pairs, we're going to go into the experiments. All our experiments were run with a BERT model for question answering. The training dataset supplied to the model was different for each experiment, but each dataset was comprised of the following components: Squad 2.0 dataset, answerable and unanswerable question-answer pairs generated by humans, answerable synthetic questions generated by unsupervised model by Lois et al., and answerable synthetic questions that we generated as part of this study. All experiments are evaluated on a held-out portion of squad question-answer pairs. We used F1 and exact match, or EM score, which are widely accepted QA metrics to compare the model's performance across different experiments. Let's briefly go over the definitions of F1 and EM scores. Exact match is a binary indicator where 1 stands for yes and 0 stands for no as to whether the predicted answer perfectly matches the actual answer. F1 score is a looser metric that measures the average overlap between the model's prediction and the ground truth answer. F1 score is a harmonic mean of precision and recall. You can see a detailed breakdown of precision and recall calculations in the context of question answering tasks on the slide. All right, now let's get into the conducted experiments and results. For the first experiment, we fed a portion of Squad 2.0 dataset to the BERT model and nothing else to establish a baseline. Note that we refrained from using the whole Squad 2.0 dataset to avoid excessive training times as we had limited access to computing power. For the second experiment, we added almost 400,000 synthetic answerable questions to the original 26,000 squad questions in the input dataset. There are way more synthetic questions than the human-generated ones because synthetic data is very noisy, so we need a large amount of synthetic training examples to produce meaningful results. Adding answerable synthetic question-answer pairs led to roughly 1% improvement over the baseline across both scores. For the third experiment, we combined 26,000 squad questions with 80,000 synthetic unanswerable questions that we generated using our model. Similarly to the second experiment, adding unanswerable synthetic questions resulted in an improvement over the baseline. The dataset for the last experiment consisted of 26,000 squad questions, 300,000 synthetic answerable questions, and 80,000 synthetic unanswerable questions. Adding both answerable and unanswerable synthetic questions to the squad training examples led to the best F1 and EM scores across the experiments. So, what do we make of these results? Firstly, we have confirmed our hypothesis. Augmenting a human-generated dataset with synthetic data does improve model performance. Specifically, we were able to improve baseline F1 and EM scores by 7% and 5% respectively for the squad question answering task. Another thing that we found interesting was that synthetic unanswerable training examples had a bigger impact on the performance than the answerable ones. This is explained by the fact that Squad 2.0 has only about 30% of unanswerable question-answer pairs, so adding unanswerable data makes the training dataset more balanced. I wanted to call out a few limitations of this study. Our approach has similar limitations to the ones present in the unsupervised model for question generation by Lewis et al. Some parts of the question generation pipeline, such as named entity recognition and subclause extraction, need some amount of human-labeled data. On top of this, our approach requires a small amount of human-labeled question-answer pairs. This limits the applicability of the approach for the domains and languages without a certain amount of pre-existing human training data. Another limitation is the extensive amount of computing power required for generating large quantities of synthetic questions and subsequently training the BERT model. Unfortunately, there is no way around it, as we have to generate a non-trivial amount of synthetic training examples because this data is very noisy. Here are a few directions that we're suggesting for future work on this study. Firstly, as I mentioned before, we were unable to conduct the experiments on a full Squad 2.0 dataset due to limited access to computing power, but it would be interesting to study performance improvements that synthetic data can bring to models trained on the full Squad 2.0 dataset. Secondly, it will be useful to look into developing a more sophisticated approach for generating unanswerable question-answer pairs to further boost the performance improvement from the synthetic data. Lastly, dividing the questions by question types and looking at performance of each category can uncover opportunities for making synthetic data even more effective. Here's the link to the GitHub repository containing the code for this project. Feel free to check it out. And here are the references used in this presentation. Alright, that's all I have for now. Thank you so much for watching.